Voyager 1 is still alive and sent NASA a terrifying message. Where is it now? In the vastness of space, there exists a silent traveler named Voyager 1, a spacecraft launched by NASA. For nearly half a century, it has journeyed through the cold expanse of space, continuously transmitting vital data from the remote corners of our solar system. However, something truly strange is happening now. Voyager 1, currently at an astonishing distance of 24 billion kilometers from Earth, has sent back alarming information that has left scientists puzzled. Could Voyager 1 be detecting something entirely unexpected during its journey through space? What mysteries lie behind the unusual signals that Voyager 1 is transmitting back to Earth, yet to be uncovered? The Voyager mission began its journey in the summer of 1977, originally planned to last only 5 years. However, both Voyager 1 and Voyager 2 defied all expectations, surprising everyone by continuing their missions for over 47 years. They have consistently transmitted critical scientific data from the outer reaches of our solar system. Initially, the two spacecraft were tasked with exploring Jupiter and Saturn, a mission they completed with remarkable success. But Voyager 1 did not stop there. The spacecraft embarked on an extraordinary journey, becoming the first spacecraft to conduct detailed observations of Uranus in 1986 and Neptune in 1989. This phase of exploration is known as the Voyager Grand Tour. In August 2012, the Voyager 1 spacecraft achieved something extraordinary. It entered a region of space beyond our solar system. This remarkable milestone occurred just 35 years after Voyager 1 began its journey from Earth. Yet, the spacecraft had even more incredible accomplishments ahead as it continued its exploration beyond the boundaries of the solar system. It wasn't until 2013 that scientists finally discovered this significant achievement. Carefully analyzing all the data sent back by Voyager 1, NASA officially announced that the spacecraft had traveled farther than anyone had imagined, leaving the Sun's influence and entering interstellar space. There, it encountered a constant stream of particles and magnetic fields, an entirely new environment for a spacecraft. Now, Voyager 1 is the farthest human-made object from Earth, traveling even farther to an astonishing distance of 24 billion kilometers. NASA's Jet Propulsion Laboratory monitors this incredible journey as Voyager 1 continues speeding away from us at an impressive velocity of about 17 kilometers per second. The Voyager missions are truly extraordinary because they have provided us with unique information about the solar system and its surroundings. These probes have been busy studying how interstellar space interacts with the continuous flow of charged particles from the Sun. The data from Voyager has also helped us understand something called the heliosphere, a protective bubble of charged particles surrounding our solar system. This bubble is shaped by the space around it. Overall, the Voyager missions have greatly expanded our knowledge and ignited excitement about space exploration. They have left an enduring legacy in space exploration, making them something we will remember for a long time. Meanwhile, experts predict that we might encounter extraterrestrial beings for the first time in 2029. They suggest that if such beings exist, they may have already received humanity's message sent through Voyager 1 back in 2002. There is immense curiosity about what might happen if Voyager 1 encounters extraterrestrial life. This scenario sparks the imagination, inviting us to reflect on the potential outcomes of such a remarkable event. The space Voyager 1 is traversing is one of the most extreme environments imaginable, far beyond what you can picture. In space, there is intense radiation, freezing cold, scorching heat, and even rocks hurtling at terrifying speeds. Almost nothing can survive there. Yet Voyager 1 has endured. But how? One of the main reasons this spacecraft has survived for so long is because it was built exceptionally robustly. Ingenious engineers designed Voyager 1 to withstand all kinds of harsh conditions, including cosmic radiation, extreme heat and cold, and even disruptive space debris. Another reason it remains operational is its unique power source, a type of nuclear battery called a radioisotope thermoelectric generator, RTG. These batteries allow the spacecraft to function smoothly, even in the far reaches of space. Voyager 1 was equipped with cutting-edge scientific instruments of its time, including a cosmic ray detector, imaging systems for high-quality photos, and tools to measure temperature. These instruments weren't just for display. They carried out serious scientific research. Voyager 1 used its scientific tools to uncover the mysteries of giant planets and their moons. Beyond capturing fascinating images, it functioned like a cosmic detective, studying phenomena such as cosmic rays, charged particles, magnetic fields, and plasma waves. As Voyager 1 journeys through space, it carries a special message from Earth for any unknown beings it may encounter. This message is the Voyager Golden Record, representing humanity's effort to communicate with extraterrestrials. The Golden Record itself is a remarkable object, made of copper and coated with gold. With a diameter of about 30 centimeters, it contains carefully curated sounds and images showcasing the diversity of life and cultures on Earth. Beyond its physical attributes, the record serves as a window into Earth's world. It tells the story of humanity and our planet, symbolizing an effort to connect with potential civilizations across the vastness of space. As Voyager 1 continues its cosmic adventure, it carries not just scientific equipment, but also serves as a messenger, representing the essence of human existence to the farthest reaches of the universe. If, by some chance, an advanced alien civilization encounters Voyager 1 and retrieves the Golden Record, it would mark a pivotal milestone in the history of interstellar communication. The Golden Record of Voyager 1 holds a mysterious fate, presenting three intriguing scenarios. First, if beings from other planets happen to encounter it, they may use their advanced technology to decode the embedded images and sounds. Second, if these beings possess the ability to travel vast distances through interstellar space or communicate across immense spans, scientists speculate that a response might reach us by 2029, potentially opening a new channel for interstellar communication. However, there is a third possibility. These mysterious beings might choose to view Voyager 1 as a relic of the past, refraining from any interaction to allow emerging civilizations to develop without interference. The impact of such an encounter between humanity and intelligence from beyond Earth would be monumental, suggesting a transformative shift that could reshape the fabric of our world. Recently, scientists have been captivated by a strange signal transmitted from the far reaches of interstellar space by Voyager 1. Previously, the spacecraft routinely sent radio signals as it drifted further from the solar system. However, in November 2023, the signal suddenly became distorted. While all health parameters sent back indicated that the spacecraft was functioning normally, the scientific data it collected from the dark and distant space beyond the solar system appeared highly unusual. At times, the NASA spacecraft seemed confused about its position in space. Occasionally, it inexplicably exited safe mode or emitted alarming signals. This has left scientists unable to open the scientific data sent by Voyager 1, and they are unsure of the source of the malfunction. Dr. Susan Dodd, project manager for Voyager at NASA's Jet Propulsion Laboratory, stated that a mystery like this is essentially a new course of study for scientists at this stage of the Voyager mission. Originally, Voyager 1 and Voyager 2 were not planned to exit the solar system, and no one expected them to still be operational after half a century, let alone continuing their journey outward. Currently, both spacecraft are in a high-radiation environment filled with mysteries no spacecraft has ever explored before. NASA is uncertain whether Voyager 1 has encountered something causing its confusion. The agency has proposed two hypotheses. Either the spacecraft is experiencing a genuine malfunction, or the region of space it has entered contains fascinating mysteries to which the spacecraft is not yet fully adapted. By March 2024, NASA engineers sent commands to the spacecraft to retrieve display data from its flight data subsystem, a system responsible for packaging Voyager 1's scientific and engineering data before transmitting it to Earth. After decoding the spacecraft's response, the engineering team identified the issue. Part of the FDS memory had failed. NASA revealed that engineers suspect a chip responsible for storing a portion of the FDS memory is no longer functioning. The root cause remains unclear. The chip may have been struck by a high-energy cosmic particle or simply degraded over its 46-year lifespan. Of course, NASA engineers cannot repair the chip directly. Instead, they implemented a solution by adjusting the software to reroute data storage to backup chips responsible for handling the spacecraft's scientific data. During the repair process from Earth, NASA continued sending mission commands to Voyager 1. Fortunately, by May 2024, they successfully received useful scientific data transmitted back to Earth. Despite the ongoing challenges facing Voyager 1, its continued operation is a relief. Interestingly, Voyager 1's signal remains strong in space, serving as a guiding beacon. Its communication system functions like a lifeline stretching from our home planet deep into space, meticulously designed by scientists and engineers to transmit data back to Earth and receive commands to sustain its mission. At the heart of this communication process lies the Deep Space Network, DSN, a global network of large radio antennas. The DSN not only facilitates the reception of scientific data from the spacecraft, but also tracks its position and operational status. Conversely, NASA uses the DSN to send commands to its spacecraft. The DSN's antennas are strategically located near Canberra, Australia, Madrid, Spain, and Goldstone, USA. These locations are nearly equidistant around the globe, ensuring continuous contact with spacecraft as Earth rotates. To maximize efficiency in space, spacecraft and probes cannot use heavy equipment that occupies excessive space or consumes large amounts of energy. Therefore, they rely on small antennas to transmit weak radio signals back to Earth, where the DSN's powerful antennas can receive them. The farther a spacecraft is from Earth, the larger the ground-based antennas must be to detect the weak signals it transmits. The largest antennas in the Deep Space Network at each location have a diameter of up to 70 meters. It is also important to note that communication with spacecraft is not instantaneous, unlike normal communications. The speed of radio wave transmission is limited by the universal speed of light, approximately 300,000 kilometers per second. For spacecraft near Earth, this communication delay is almost negligible. However, at greater distances from Earth, the delay can become a significant challenge. For example, when a spacecraft is near Mars, the planet is about 55 million kilometers away from Earth at its closest point, resulting in a delay of around 4 minutes. At the farthest point, when the two planets are over 400 million kilometers apart, the delay can be as much as 24 minutes. This means that a message from the spacecraft would take 4 to 24 minutes to reach mission control and an additional 4 to 24 minutes for the response to return. Voyager 1 is the farthest object the Deep Space Network maintains contact with. The Voyager spacecraft uses a 23-watt radio, significantly more powerful than the 3 watts used by a standard mobile phone. However, given the spacecraft's immense distance, it is still an extremely low-power transmitter. By comparison, large radio stations on Earth transmit at tens of thousands of watts, and even their signals fade quickly. For Voyager, the key to receiving its signal is not the radio's power, but the combination of 3 factors: large antennas, precise alignment with the deep space network, and minimal interference from other signals. Unlike other spacecraft, which typically have 2 to 3 meter antennas, both Voyager spacecraft are equipped with a high-gain antenna, measuring 3.7 meters. This antenna points directly at a 34-meter antenna on Earth and transmits signals in the 8 GHz frequency band. This frequency is rarely used, allowing ground antennas to employ extremely powerful amplifiers to detect signals from Voyager without the risk of interference from other transmissions. On the Earth-to-space transmission side, the deep space network, unrestricted by power limitations, uses tens of thousands of watts to ensure that spacecraft like Voyager receive commands. Because Voyager is more than 24 billion kilometers, or over 22 light-hours, away from Earth, the signals received by the deep space network are incredibly faint. The energy received from Voyager is more than 20 billion times weaker than what is needed to power a digital wristwatch. Nevertheless, thanks to the sparsely used frequency band, NASA engineers can amplify the signal to make it loud and clear. The centers at each Deep Space Network site receive signals from Voyager and relay them to the Spaceflight Operations Center at NASA's Jet Propulsion Laboratory in California. Here, images and other data are processed and shared with scientists and the public. To date, the Voyager mission has provided invaluable insights into the outer reaches of our solar system. The spacecraft serve as symbolic beacons of hope, representing humanity's relentless effort to understand the universe and our place within it. Beyond the cosmic horizon, we are living in a vast dimension with an estimated age of about 13.8 billion years. We know this because the oldest visible light ever observed by scientists dates back to approximately this time. The farthest light we can see in the universe defines the boundary of what we consider the observable universe. Even as the universe expands at the speed of light, the observable universe should have a maximum diameter of about 28 billion light-years, based on its age. However, with scientists' estimates of redshift, it appears that our observable universe is 3 times larger than that size, with a diameter of approximately 93 billion light-years. What lies at the edge, or truly beyond the intricate boundaries of this observable universe, remains a mystery. But something even larger lurks behind the twilight curtain. Thanks to redshift analysis, scientists know that some galaxies are moving away from us at speeds greater than the speed of light. Even though the oldest light from these galaxies is still being emitted and has only just reached us, we now know that these galaxies have already disappeared beyond the cosmic horizon. These regions of space will never be accessible again. But how is this possible? Why does the universe expand faster than the speed of light? Why are distant galaxies moving away from us in the first place? And more intriguingly, why do they accelerate as they surpass the speed of light? Why do so many truths of astrophysics seem to be challenged when we begin to peer towards the edges of space? The so-called observable universe is a spherical region independent of the structure of the entire universe, containing all the light and matter we can observe here on Earth. The observable universe has become synonymous with our study of the cosmos, but every point in space has its own observable universe. Thus, there is a barrier, and once this barrier is crossed, everything becomes invisible from any specific point. as light has not had enough time to reach that region. This boundary is known as the cosmic event horizon. Our observable universe expands at the speed of light. Therefore, any anomalies that vanish beyond the cosmic horizon must theoretically travel faster than light to escape our view. This should be impossible according to the theory of relativity. Yet, this is precisely what an estimated 96.4% of all the galaxies we have ever observed have managed to do. The light reaching us today essentially illuminates a three-dimensional hologram of galaxies. While a continuous stream of visible photons is something that will certainly occur for billions of years to come, the galaxies in question are now inaccessible to us by any known method of travel according to the theory of special relativity. However, their older light serves as a kind of replay of the past, looking toward the edge of the observable universe to find this early light is incredibly useful for us here on Earth, providing a transparent lens into the distant past of our universe. This not only helps us estimate their age, but also allows us to piece together their life cycle by examining their different stages of development. We often observe black holes swirling gas in their accretion disks, forming quasars during the earliest epochs of light in history. We also see young galaxies and, overall, a more chaotic and unpredictable universe. Our observable universe is estimated to have a diameter of 93 billion light-years. But the farthest objects we have ever observed before the cosmic horizon seem to lie about 46 billion light-years away. Why is this the case? Why does this unanswered question persist? How can the observable universe be larger than the age of the universe multiplied by the distance light travels? This is a challenging concept to grasp. When observing stars in our galaxy, there is always a consistent and unchanging delay. Light emitted from the neighboring star, Proxima Centauri, takes approximately 4 years to reach us, and this is a fixed, consistent delay. However, with observations beyond our galaxy, there is no consistent delay. Our universe is expanding at different rates, depending on what it has experienced: matter, dark energy, radiation, and so on. And we ourselves are moving through space. Thus, light emitted from an object that was once very close to us has traveled through an intergalactic journey, traversing this ever-expanding space to finally reach our eyes approximately 13 billion years later. Currently, scientists estimate that galaxies and many other celestial bodies at the edge of the observable universe are as far as 46 billion light-years away, and their light will never reach us now because they have crossed the boundary of the speed of light. The age of the universe no longer cooperates with this limit. Beyond this barrier, the universe becomes causally disconnected from the observable universe, fragmented, segmented, and severed. This explains why MAX 0647-JD, a galaxy once holding the record as the farthest observed galaxy at 13.3 billion light-years away, appears remarkably young and small for its age. According to hypotheses, it formed very early in the universe, just a few 100 million years after the Big Bang. Yet the light it emitted has undergone a massive intergalactic journey through the expanding cosmos to reach us. This observed phenomenon of accelerated expansion could imply that there might be up to 2 trillion galaxies for us to observe in the future, far exceeding the previous estimate of several 100 billion galaxies that we once believed. In the future, our observable universe is expected to expand, and our view is anticipated to broaden. But remember, there is a clear distinction between the observable universe and what we call the accessible universe. The accessible universe refers to the region within the cosmic horizon, where we can still reach distant stars and possibly objects beyond galaxies, given enough time. Beyond the cosmic horizon, no one truly knows what lies there. We don't know what really happens to galaxies as they pass beyond the horizon. While scientists assume that it is similar to what we observe, stars, galaxies, planets, and black holes, we don't know if there is anything beyond that, whether it's just a vast empty void or some physical edge. It is possible that many similar cases exist beyond the boundary. And if you think the observable universe, stretching 93 billion light-years, is immense, the uncharted expanse will truly blow your mind. At 93 billion light-years, the observable universe seems almost incomprehensibly vast. But then you realize that its entire scope barely scratches the surface of the completely isolated universe beyond the barrier. While we may never know for sure, it is highly likely that the expansion beyond the cosmic horizon could be hundreds, thousands, or even millions of times larger than the observable universe. But the question remains, how is this possible? The universe was not supposed to be anywhere near this large. In fact, up until recently, as it approaches the halfway point of its lifespan, we thought the expansion might even have started slowing down. The current estimated rate of expansion of the universe is about 68 kilometers per second per megaparsec. This expansion is not a uniform sphere. It's empty space stretching in all directions due to unknown natural forces. Although the universe expands at a rate of 68 kilometers per second, this rate is measured per megaparsec. A megaparsec is a unit of distance equivalent to about 3.26 million light-years. Thus, for every 3.26 million light-years farther from us, the expansion rate of the universe appears faster. For example, just over 6 million light-years from Earth, the universe is expanding at a rate of approximately 204 kilometers per second. In regions between galaxies, this recession velocity reaches extremely high speeds, eventually exceeding the speed of light at distances far enough from us. Of course, the laws of special relativity state that nothing can move faster than the speed of light. However, special relativity is a local domain. At present, you cannot personally board a spaceship and travel faster than light. But when comparing and contrasting the distances between galaxies, this limitation becomes much less apparent. The measurements themselves are not excluded, but this is only the apparent speed of receding galaxies. We still don't understand why space itself is expanding faster than light, or why the universe is unimaginably larger than expected. It is thanks to the receding galaxies that this question was raised in 1998, and it prompted a group searching for supernovae, the High-Z Supernova Search Team, including 3 members who later won the Nobel Prize to investigate this issue. They concluded that the universe experienced most of its unexpected growth during the latter half of its lifespan. Before that, the universe's expansion was actually believed to be slowing down due to the gravitational pull of large masses from within. But then came a period in the universe's life known as the dark energy-dominated era, which began approximately 6 billion years ago. Dark energy is a fascinating concept about which we know very little. You may have heard the terms dark energy and dark matter used interchangeably. However, while dark matter is a form of matter that may consist of some undiscovered type of particle, dark energy is an unknown form of energy existing within the vast, empty regions of the universe. Under general relativity, the accelerated expansion of the universe can be explained by a positive value in the cosmological constant, an equation proposed by Albert Einstein to define the energy density of space. This positive presence can also be described as vacuum energy, which is more commonly referred to as dark energy. Although we have never directly observed dark energy, we have seen light distorted by gravitational lensing in areas that appear to be empty. This suggests that dark energy does not seem to interact with ordinary baryonic matter that we know and appears only to be influenced by gravity. Dark energy may not even be a physical presence in itself, and could merely be a property of the vast emptiness of the universe. If not, it is thought to be highly dynamic and have low density. Dark energy is evidenced by the need for an additional form of energy, neither matter nor dark matter, because the universe seems to have expanded significantly more during the latter half of its lifespan. Essentially, there must be something driving this faster-than-light expansion. Large-scale mass-density wave patterns also provide evidence supporting the existence of dark energy, but they tell us nothing about why it exists, why it pushes space apart, why it moves faster than the speed of light, or why it only manifests in the dark. We only know the mathematical equations that allow us to infer its nature. Assuming current cosmological models are accurate, dark energy is estimated to make up as much as 2/3, or even all the energy in the observable universe. Now, compare that to the 27% of dark matter, and the mere 5% of matter that we know and understand. Putting aside these haunting questions, if dark energy is indeed driving the rapid expansion of the universe beyond the speed of light, how vast is it? Not just the observable universe, but the total universe. There are many conflicting theories, ideas, and a wide range of estimated values. One theory, which conflicts with the idea of a larger unobservable universe, suggests that the universe may only have a diameter of about 78 billion light-years. N. Cornish and his collaborators published a paper claiming that the universe might only span 98.5% of the predicted range of the cosmic microwave background (CMB) map. However, their testing on the CMB found no evidence of a finite boundary at such a distance. Even so, some still believe that the observable universe could equal or even exceed the size of the total universe. Why do we see galaxies beyond the estimated size? It has been theorized that this could be due to reflections. If the universe curves back on itself, photons might hypothetically loop around due to gravitational effects at the universe's edge. With hundreds of billions of distant galaxies in the observable universe, there is no way to pair a galaxy with its possible reflected image, nor to confirm whether we have found a true galaxy or a reflection. That said, more evidence contradicts these theories than supports them. Other estimates suggest sizes ranging from 250 billion light-years to 180 billion light-years, sometimes incorrectly inferred by mistaking diameter for radius. A more stringent experimental method involves measuring the positive and negative curvature of what we believe to be a flat universe in space. This was the purpose of the Sloan Digital Sky Survey and the WMAP satellite, both of which concluded there is no measurable curvature from the space surveyed. The observable universe might be as small as 0.25% of the radius of the entire universe. No significant curvature has been detected, suggesting that a much larger area would be required for any anticipated curve. This implies an astounding radius of 23 trillion light-years, with a mass over 15 million times that of the entire observable universe. The frightening part is that this estimate might actually be quite pessimistic. The true size could be significantly larger than even a radius of 23 trillion light-years. If we follow the current estimates to their logical conclusion, we arrive at the theory of an infinite universe with vastly different absolute dimensions and mysteries surrounding dark energy. Some believe that the entirety of the unobservable universe could, in fact, be infinite. After all, if it is expanding, what lies beyond it? It is hard to believe that there is simply nothing outside of an arbitrary boundary. And if the Big Bang truly happened everywhere, why couldn't the universe be infinite? As the numbers grow and estimates become larger, more people are adopting the theory that the universe beyond what we can observe may indeed stretch on forever. Nevertheless, the expansion of the universe remains an elusive concept. Technically, The universe isn't expanding into anything, and no external void is needed for the interior to grow. This idea truly boggles the mind. Space itself is incredible, and it may harbor even stranger and more challenging physical properties in its darkness. Scientists explode with excitement over the functionality of the new light-speed engine. When it comes to space travel, one persistent problem is movement across the vast expanse of space. Even traveling at the maximum speed allowed by the universe, it would take us years to reach the nearest neighboring star. As Elon Musk put it, if we don't improve our progress soon, humanity will surely perish before we ever reach Mars. Yet, humans are remarkably skilled at solving big problems, and that's exactly what NASA engineer David has been working on. David has conceptualized an engine that, in theory, could accelerate up to a significant percentage of the speed of light, all without using any propellant. If successful, this seemingly insane idea that breaks the laws of physics could entirely revolutionize how NASA or any other space agency in the world builds spacecraft. But if there's no propellant, how would this engine function? Dr. Percy unveiled this concept in a groundbreaking paper published on NASA's website under the title Helical Engine. Although it has faced skepticism from some, Percy believes that his concept is worth pursuing. I'm comfortable putting it out there. If someone proves it doesn't work, I'll be the first to say it was worth trying, said Dr. Percy. According to him, the true purpose of the so-called helical engine is to enable travel to distant stars much faster than any existing technology. In his paper, he explained that this space engine could be used to maintain long-term satellite stations without needing additional propellant. It could also propel spacecraft across interstellar distances, nearing the speed of light. Traveling at such speeds, theoretically, could enable astronauts to experience conditions where light struggles to keep up, bending their vision in strange ways. Everything behind them would appear black, and time itself would seem to stop entirely. Clocks would slow down, and planets would appear to cease rotating. At first glance, many may dismiss the idea as absurd, but we shouldn't judge a book by its cover. Let's explore Dr. Percy's detailed explanation of this light-speed engine that operates entirely without propellant. Today's rockets, such as those built by NASA and SpaceX, require tons of propellant, like liquid hydrogen and methane, to carry humans to Mars and beyond. The issue is that the more fuel you add to a spacecraft, the heavier it becomes. Modern propellant tanks are far too cumbersome for interstellar travel. Therefore, it's safe to say that if successful, Dr. Percy's concept, seemingly straight out of a mad scientist's lab, could spark a revolutionary breakthrough in rocketry. The helical engine would utilize high-tech particle accelerators, generating accelerated particles similar to those found in the world's largest high-energy particle collider. This technology could overcome the reliance on any type of propellant. Small particles are heated at high speed using electromagnets. Then they spin around the engine and are fired back. According to Dr. Pearl, this exploits a loophole in the laws of physics. In theory, the engine could achieve speeds of approximately millions of meters per second. Simply put, the engine works by taking advantage of how mass changes at the speed of light. To explain the helical engine in a more straightforward way, David describes a box placed on a frictionless surface in a vacuum environment, similar to the illustration shown here. Inside the box, there's a small metal ball suspended on a string, continuously oscillating due to two springs attached to opposite walls of the box. In the vacuum of space, this effect would cause the entire box to vibrate, while the weight remains stationary. The box would continuously vibrate at a fixed point, but if the mass of the weight continuously increases in one direction, it would generate a thrust force. This is the force that would propel the box forward. As described by Einstein's famous equation E equals mc squared, mass and energy are essentially the same entity and can be converted into one another. Following this reasoning, the energy a moving object gains will increase its own mass. In other words, the faster an object moves, the greater its mass becomes. However, this increase in mass is only noticeable when the object is moving at an extremely high velocity. Specifically, as an object approaches the speed of light, its mass grows exponentially. If an object were to reach the speed of light, its mass would become infinite, requiring an infinite amount of force to keep it moving. For this reason, no ordinary object can move at or faster than the speed of light. This effect is accounted for in particle accelerators. In practice, a simplified implementation of David's concept involves replacing the metal ball with ions and swapping the box for a particle accelerator. In this scenario, ions would move faster in one half of the loop and slower in the other half. David suggests it would be more practical if the accelerator used in the engine was shaped like a stretched spring, hence the name helical engine. This engine would accelerate ions in a loop at an average speed, and then vary their velocity to simultaneously alter their mass. Once reaching a specific velocity, the engine would direct the ions to move back and forth in a defined direction to generate thrust. NASA scientists believe that the helical engine has eliminated the heaviest component of a spacecraft, its fuel. Therefore, this engine could theoretically achieve a maximum speed close to the speed of light. Sounds amazing, doesn't it? But that's only in theory. In practice, the concept faces several challenges. For the engine to work, it would require the same material used to type on a computer keyboard. And most importantly, it would only be able to achieve near-light speeds in a frictionless environment. Dr. Percy stated that the engine itself would need adequate time and energy. Proposals for new engines that use less propellant, such as the helical engine, are promising. However, Robert Cook, an American inventor, was granted a patent for an engine that supposedly converts centrifugal force into linear motion. Later, Roger Scheuer proposed the EM drive, which he claimed could convert trapped microwaves into thrust. Both concepts have failed to demonstrate success and are widely considered impractical because they violate the law of conservation of momentum, a fundamental principle of physics. Martin Tajmer of the University of Technology in Dresden, Germany, who has conducted experiments on a model of the engine, believes the helical engine could face similar issues. He stated, "All inertial propulsion systems, as far as I understand, never work in frictionless environments." He further added that this machine utilizes special relativity, unlike other systems, which complicates the picture further. But unfortunately, for every action, there will always be an equal and opposite reaction, he noted. David has been working on his design independently without any funding from NASA, and he admits that his idea is highly inefficient. However, he also claims that it is possible to recover much of the energy lost by the accelerator to heat and radiation. He suggested ways momentum could be conserved, such as through the spin of accelerated ions. Dr. Percy remarked, "I know my research runs the risk of facing the same problems as the EM drive, but you have to be ready to be ridiculed for making mistakes. It's really hard to invent something entirely new under the sun that actually works." So far, what David has is a foundation capable of supporting the development of such an engine. However, with the rapid advancements in aerospace technology, we shouldn't be too surprised if a light-speed engine emerges in the near future. Many things that once seemed crazy and existed only in science fiction have already been invented and applied in real life by humanity. Creating a light-speed engine is just one of the many challenges humans must overcome. To travel at the speed of light, an immense amount of energy is required. Currently, no technology exists that can produce the necessary energy to power a light-speed engine. The materials needed to build a light-speed engine must meet extremely high standards for durability, flexibility, and resistance to light. At present, we do not have any materials capable of meeting these requirements. Controlling a light-speed engine to move at the speed of light is also incredibly complex. We need to figure out how to control the engine with extreme precision to avoid accidents and collisions. At light speed, objects will encounter numerous environmental effects, such as spatial distortion, radiation, and the surrounding materials. We need to find ways to mitigate these effects to ensure the safety of those operating the engine. In conclusion, traveling at the speed of light is a monumental challenge for humanity and requires solving many technical and scientific issues to make it a reality.